So in order to complete a Hardy Weinberg problem, we have to use statistics. And this isn't a statistics course, so what we're going to do is a crash course into statistics so that you basically understand the overview of statistics and kind of what statistics is, and then it'll help you to better understand what exactly we're doing to solve a Hardy Weinberg problem. So to kind of recap where we are from the last video is we were working through a Hardy Weinberg problem and we were able to solve that our population should look like the values you see here. And we compare those to what we actually saw, which are the values below it. And so the question is are these numbers close enough to be considered the same? Is 4.51 the same number as 4? I mean, technically, no, they're not the same number, but they are pretty close. Is it close enough to say, yeah, those are pretty equal, or are they different enough to say, you know what, something might be going on here. This isn't what we expected. And so we can actually use the field of statistics to answer that question. Is one set of numbers similar or different to another set of numbers? So let's think about statistics as a whole first, mainly because as a biologist, you're going to use statistics a lot. So all statistical tests use something called a null hypothesis. You're probably familiar with the idea of a hypothesis, an educated guess. But a null hypothesis is kind of that null part. Null meaning nothing, zero, void. So a null hypothesis says nothing's happening. And what statistics will do is tell us how likely is it that nothing is happening. Now you're going to see, not just in this video, but anytime you really come across stats, you'll see null hypothesis kind of indicated with this H sub 0, that 0 kind of representing the null part of things. So let's do an example. Imagine your research question, unrelated to Hardy Weinberg, is, are there more grasshoppers in forests or wetlands? Now you might have a hypothesis, oh, I think they'd be more common in forests. But the null hypothesis, remember, is that there's nothing going on. So my null hypothesis for this question would be something like, there is a similar amount of grasshoppers in forests or wetlands, right? There's nothing happening. Wetlands aren't higher, forests aren't higher. We're just going to say nothing's happening. Later, we do a statistical test, and it's going to tell us how likely is nothing happening. Another question, is there a relationship between temperature and hurricane frequency? Again, a null hypothesis, nothing is happening, would say no, there is no relationship between temperature and hurricane frequency. And then finally, if we want to bring this back to Hardy Weinberg, you could have a question such as, is the koala population evolving? Again, null hypothesis, nothing is happening. It is null, it is void. So the koala population is not evolving. Or you could say the koala population is in Hardy Weinberg equilibrium. Remember, Hardy Weinberg equilibrium says the population isn't evolving. So all statistics, whether it's Hardy Weinberg testing or any other testing, relies on a null hypothesis. Now, statistical test is honestly just a whole bunch of algebra, and it just tells us something statistically. So there's different types of tests depending on your data, but no matter what your question is, no matter what your data is, all statistical tests are going to lead to a single value. And this value is called the p-value. And the p-value, the p stands for probability. It's essentially what's the likelihood your null hypothesis is correct. P-values range from 0 to 1. So 1 would be the same as saying 100%. So if you had a p-value of 1, you're saying there is a 100% chance your null hypothesis is correct. So it's probably correct. There's nothing going on in your system. Now, sure, you can get a p-value, and that kind of tells you a likelihood of how likely your null hypothesis is correct, but at what point do you say, yes, something's happening, or no, nothing is happening? We need a threshold. Like, what's the magic value that determines if something's happening or not? So this threshold is referred to as an alpha value. And the most commonly used alpha value, this is not just for biology, but chemistry, physics, sociology, psychology, honestly any field that ever uses statistics is likely using a threshold of 0.05 or 5%. So when we say threshold, here's how we interpret that threshold. So if your p is less than alpha, so less than 0.05, we're saying that there's a less than 5% chance your null hypothesis is correct. That's pretty small. You know, if your p was 0.01, you're saying there's a 1% chance my null is correct, meaning there's a 99% chance something else is going on. At that point, we're going to say, you know what? We're going to reject our null hypothesis. Something's going on in this system. There's more grasshoppers in wetlands. Koalas are evolving. There is a relationship between temperature and hurricane frequency. Now, if your p-value is greater than your alpha or greater than your threshold or greater than the standard 0.05, we would say there's a greater than 5% chance that null is correct. And we're saying, that's too high for us. Like, we don't want to say something's going on. That threshold, it's not quite there. You might be like, well, it's 0.06, it's only 6%. You got to draw that threshold somewhere. So if we say there's a 5% chance or greater than 5% chance the null is correct, we say we fail to reject the null hypothesis. Now, that double negative can sometimes be hard to kind of wrap your brain around. More or less, you're accepting the null. There's nothing going on here. In science, we really don't like the words like accept or prove. We more like to reject things or support things. And it's mainly because we recognize we have not gathered every single piece of data. We have not tested something 100% of the way. Science is meant to be disproven, so we don't like to accept things or prove things. So again, if it's greater than that threshold, we're going to fail to reject our null. So more or less we're saying, okay, there's nothing going on here, or at least there's not enough data to support that anything's going on here. Now, sometimes, I mean, there's a lot of numbers and it's like bigger or less than or whatnot. This is something I learned when I was a student. My professor taught us. So a little small thing of remembering which way things are. And that's what I have written here. If p is low, reject the ho. And when I say ho, I mean h sub 0. So if p is low, so lower than that alpha, reject the ho. One last thought before moving on. While 0.05 is like the most common alpha value, it can be different. For example, if you're doing medication studies, your threshold might be a lot lower. You might want to be super sure that that medication is actually working before releasing it onto the market. So do know alpha can definitely change, but it's usually in very limited capacities. For the most part, you're always going to see it set to 0.05. If it's not reported in a paper, you can assume it's 0.05. So everything we talked about was kind of like general statistics. All statistical tests are going to use a null hypothesis. All statistical tests will end with a p-value. Now, very specifically, when we're testing values and doing a Hardy Weinberg problem, the type of statistical test we're going to use is called a chi-square statistical test. Now, we are not going to explore in this video why this test was chosen. In general, I will tell you it's the type of data you have and how much data do you have, and honestly, how is that data distributed, that will impact your statistical test. But I don't care about that. I just want you to know you use a chi-square test. And so we'll use this chi-square test that you see here to compare what did we observe and what did we expect. So to kind of briefly explain how this equation works, so the variable you're solving for is chi-square. Do want to emphasize you're solving for chi-square, not chi, like don't square root anything. Chi-square stays together. Equals sigma, remember that means sum. of your observed value minus your expected value divided by your, squared divided by your expected value. So your observed values are going to be, what did the problem give you? What was your population actually like? Your expected values are, you plugged it into the Hardy Weinberg equation and you got these different expected number of individuals. If your population was in Hardy Weinberg equilibrium, what would your population look like? So this video is just kind of doing the overview. In the next video, we'll go a little bit more on like how you plug those numbers in. But let's just say we had a data set, we plugged it into the chi-square equation, and we solved for chi-square, in this case being 1.268. Cool. But I told you earlier, all statistics ends with a p-value, and we are not at a p-value. We got a chi-square value. Cool, but it's not a p-value. We can't directly evaluate this. So if you take a statistics course, something you will learn very quickly is in the very back of your statistics book, there are these tables. And we're talking about pages and full pages of statistics tables. And these tables, more or less, are to convert your test statistic, so in this case our chi-square statistic, into a p-value. And then you can evaluate your p-value. So here I've given you a quick, small snippet of a chi-square table. Along the top, it says probability level or alpha. You can essentially interpret this as p-values. Remember, alpha is a p-value. It's just your threshold value. So here we've got 0.5 all the way to 0.001. Remember that 0.05 is kind of the industry standard. So that's along the top. Along the side are DF, or degrees of freedom. And then all these numbers in the middle here, these are all chi-square values. So what you're trying to do is figure out where your chi-square value is in this table. To do so, you first need to determine how many degrees of freedom you have. Now, degrees of freedom is actually used in a lot of statistical tests when you get to this point, looking at the statistics table. So degrees of freedom is simply how many variables do you have and subtract 1. So you might think, oh, well, we have 3 variables, right? We have p squared, 2pq, and q squared, or big R, little r, little r, little r. 3 variables minus 1 is 2. And that's not a bad line of thinking, but big R, little r, little r, little r, aren't there only 2 variables, big R and little r? We just did different combinations of them, but at the end of the day, it's only 2 variables. It's only 2 numbers. There is a number for big R, and there was a number for little r. There was a number for p, and there's a number for q. So when it comes to a Hardy Weinberg problem, our degrees of freedom is actually 2 variables minus 1, meaning it's just 1 degree of freedom. Now, for those of you in my class, I don't really care if you know degrees of freedom or not. If you want to just memorize Hardy Weinberg, degree of freedom of 1, that's totally fine. All right, so we're going to look in this row where the degrees of freedom are 1. We are looking to see where does 1.268 fall within this row. So it's going to fall here between 0.455 and 2.706. So 1.268 is going to fit in here, meaning it's between our p-value. If I go back up, our p-value ranges between 0.5 and 0.1. So then the last thing we do is just evaluate that. If it's between 0.5 and 0.1, isn't that larger than 0.05? We're saying our likelihood, our null hypothesis is correct, is higher than our threshold, meaning, you know what? Nothing big's going on here. This population isn't evolving. This population is in Hardy Weinberg equilibrium. So with that kind of gives you everything you need to know to get started with statistics and at least understand the statistics behind Hardy Weinberg. In the next video, it's going to take the information learned from this video and apply it back to the Hardy Weinberg problem that we've been following along.